Hi, good day, everyone. My name is Ahmad Pridaus, and today we're going to present the seminar for the machine vision and image processing. So our team consists of two people, two-person. That is myself, Ahmad Pridaus bin Idrus, and Om Prakash Rangasamy. So the student ID is 21000506 and 22009776, respectively. So this is a seminar covering advances in the AI that solve key tasks in machine vision and image processing. Together with the seminar, we have prepared a tutorial that is uploaded by a teammate, Prakash, in a different URL. So for the seminar, we have divided these into three sections. That is, the first one is the image restoration or denoising. Second one is image classification and object detection. Third one is comparison of the traditional algorithms versus the deep learning. Now, without further ado, let's proceed with section one, image restoration and denoising. So we've done the tutorial on the in the separate video. This is the tutorial one, image restoration or denoising. We're gonna go to the noise to noise. That is the learning image restoration without the clean data. The noise to noise approach is presented, which is a deep learning based method for image restoration and denoising. The key idea behind noise to noise is to train a neural network to learn the mapping between pairs of noisy images without the need for corresponding clean reference images. The network exploits the redundancy present in the data to estimate the true signal while ignoring the noise. This self-supervised learning approach has shown impressive result in restoring images and removing noises from various types of data. Here, example here, the photo of this noise to noise learning image restoration without the clean data. And next, we're going to the part two, that is noise to void, the learning denoising from single noisy images. So noise to void is presented, which is another deep learning based approach for image denoising. Unlike noise to void is a self-supervised technique that does not require paired clean images during the training. This is designed to handle single noisy images directly. The network is trained to predict missing information without the image by considering the surrounding context. The noise to void has demonstrated its effectiveness in denoising microscopy and other types of noisy image data. Here's some snapshot from the learning image restoration without the clean data. Here we can see the better sampling of the underlying manifold in the same capture. And here an example of image of 8 samples per pixel. This is another clean image that is 64,000 samples per pixel. And this is what we've done in the tutorial, image enhancements. We can see that three images, the original, noisy image, and the noise image. These can be viewed in the separate tutorial video uploaded by our team. Now, we're going to go to the section 2, that is the image classification and object detection. Okay, the part 1 is the vision transformer. An image is worth 16 times 16 words. So transformers for image recognition at scale, so to say. So this introduced the vision transformer VIT model, which applies the transformer architecture initially designed for natural language processing to image recognition tasks. Vision transformer divides the input image into a small non-overlapping patches and linearly embeds them to create a sequence of tokens. These tokens are then passed through multiple transformers layer, allowing the model to capture long-range dependency, and global information in the image. Vision transformers have achieved impressive results in image classification tasks and has the potential to scale to large data set. We're going to the part two, that is end-to-end object detection with transformers. So there's a video that need to be watched in a separate link. The end-to-end object detection with transformers, or simply DETR model, is presented. So DETR is a novel approach to object detection that eliminates the need for complex region proposal mechanism used in traditional object detection pipelines. Instead, DETR directly predicts the set of object bounding boxes and their corresponding class label in one shot. It achieved this by formulating the object detection as a set prediction problem using a bipartite matching laws to assign prediction to the ground truth object. DETR has shown promising results in object detection while simplifying the overall detection pipeline. Okay, we're gonna go to the part three, that is a segment anything model, SEM. So that's a paper provided with the title Segmenting Anything with Adaptive Instance Normalization. In this paper, it talks about the segment anything model, that is a novel approach to image segmentation. SAM aims to segment various objects in images without relying on specific annotation or predefined classes. It treats images segmentation as a self-supervised problem and utilizes a novel framework that combines adaptive instances, normalization, and clustering. SAM has demonstrated its ability to perform unsupervised segmentation and shows promise in segmenting objects with diverse appearances. Okay, that's it for the image classification and object detection. That's a tutorial tool that we've done on this. Then we did with the histogram of oriented gradients, HOG. This is the snapshot of it. You guys can watch this in a separate tutorial video that we have uploaded. This is the example, this is the original image, and this is the histogram representation. But I'm not sure whether you guys can see clearly on the screen, but here's the figure. All right. Now, we're gonna proceed to the third section, that is the comparison of the AI-enabled machine vision applications versus the standard image processing and machine vision algorithms. Comparison. For the traditional algorithms, this traditional computer vision algorithm, as covered in the tutorials, often involve handcrafted feature engineering and use various techniques such as filtering, edge detection, and feature extraction to process the images. So they can be computationally efficient and are suitable for simpler tasks that do not require extensive training of data. However, they may struggle with complex tasks where feature engineering becomes challenging or when dealing with a large scales of data set. Now, deep learning approaches. So through these deep learning approaches, we've learned, and then we understand that the cutting edge deep learning methods that have shown significant improvements in various computer vision tasks. Deep learning models such as noise to noise, noise to void, VIT vision, and then the DETR have the ability to automatically learn relevant features from the data, reducing the need for handcrafted feature engineering. These methods often require a larger amount of data and more computational resources for training, but they have demonstrated the state-of-the-art performances in tasks like image restoration, denoising, classification, and also object detection. So, um, the audience, ladies and gentlemen, deep learning approach are particularly effective when dealing with complex data and tasks that require capturing long-range dependencies and global context information. Now, we have a summary here. Sorry, this is eight point form that we like to highlight in the comparison for this enable AI enable and the standard image processing. The first one being the adaptability. So in the AI, it can adapt to new data and environments without extensive manual tuning. Whereas for the standard algorithm, it may require more manual tuning for different scenarios. And then next, the second one is the aspect of accuracy. For the AI, it achieves higher accuracy rates in the complex visual tasks due to the deep learning capabilities. And then in comparison, the standard, the accuracy may be very low or lower in some cases, especially for the complex tasks. The third one is the feature extraction. So this is for the AI-enabled machine, they automatically learns relevant features from the data, reducing the need for the handcrafted features engineering. On the standard image processing, however, often requires manual feature engineering to extract the relevant information from the image. And number four is the real-time performance. For the AI-enabled machine, it can achieve real-time or near real-time performance with advancement in the hardware and model optimization. However, for the standard image processing, it may have a faster processing because of the simpler algorithm and lower computational requirement. Now, another four is the fifth here is the data dependency aspects. For the AI-enabled machine vision, it requires a large amount of label training data, which may be expensive and time-consuming to acquire, while the standard image processing has some standard algorithms that can work effectively with just a smaller data set. And number six here, the computational intensity. So for the AI-enabled machine, the training complex deep learning models demand significant computational resources, while the standard require less computational power, making them suitable for the resource-constrained devices. Now, the seventh one is the aspect of interpretability. The deep learning model can be considered black boxes, making it challenging to understand their decision-making process. However, for the standard image processing, it is more interpretable, allowing users to understand the reasoning behind the decision. And the last, number eight, that we've compiled here is that the aspects of vulnerability to adversarial attacks. For the AI-enabled mission vision, it may be susceptible to the adversarial inputs, where carefully crafted perturbation can lead to the misclassification. And this is for the standard image processing. The algorithms are more robust against the adversarial attacks. Okay, well, that's it. That is the end of the seminar. If you guys have any further question, you can write to our mail, our UTP mail. Both of us, we are glad to answer this. That's it. So to conclude, our thought is that while traditional computer vision algorithms remain useful for specific tasks, deep learning approaches offer a powerful and flexible solution for a wide range of computer vision challenges, especially those that involve complex pattern and large data sets. That's it. Thank you, everyone.